Hello and welcome to our lesson on making salts. Last lesson, acids and alkalis and neutralisation, we looked at the concept of a neutralisation reaction where any acid plus any alkali will make a salt and water. And this lesson, we're going to focus on this word salt. So what is a salt? Well, it's not just the stuff you put on your fish and chips. There's many types of salts, and this is why. So if you look at the example in the diagram, here you can hopefully recognise I have got the ions involved with hydrochloric acid, HCl. Now in a reaction, if that hydrogen ion is displaced or removed or taken away, and a metal atom or a metal ion, is taking its place, you would make a salt. In this example, this is potassium chloride. So a salt by definition is a chemical in which the hydrogen from an acid has been replaced by a metal. Now, of course, there are many metals on the periodic table, and that means then there are many different salts that can be made. So, for example, if I remove this hydrogen, here's a metal, this is lithium chloride. However, if I use iron, I have iron chloride, zinc chloride, sodium chloride. And if I change the acid, so hopefully you recognise here this is sulfuric acid, H2SO4. Again, if I remove that hydrogen and I replace it with a metal, this time this is lithium sulfate, or iron sulfate, or zinc sulfate, or sodium sulfate, and it can go on and on. You know the periodic table is what, 2/3 metals, so there's loads and loads of options. And of course, there's not just two acids, there's many different types of acids. The ones we learn about, hydrochloric acid, sulfuric acid and nitric acid, but citric acid, ethanoic acid, formic acid, there's all sorts of acids, and so the number of salts that we can make is almost endless. How do we use this then? Okay, so pause the video and have a go at naming the salts that are made in each of these reactions. Okay, so the first one then, hydrochloric acid plus sodium oxide. Well, sodium is my metal. If I wasn't sure, I'd be looking at my periodic table. Sodium is group 1, and it's going to be sodium chloride plus the water because it's a neutralisation reaction and we make water every time. Second one, hydrochloric acid plus iron hydroxide. Well, again, I'm going to make, so my metal is iron, so it's going to be iron chloride plus water. Thirdly then, I've got hydrochloric acid plus tin oxide. Tin is my metal, so it's going to be tin chloride plus water. And finally, hydrochloric acid plus lithium hydroxide. Lithium is my metal, group 1, and so it's lithium chloride plus water. Okay, so this time I have changed the acids. Have a think. If in doubt, sound it out in your head what sounds right. Copper sulfide, copper sulfate, copper, what sounds right, because 9 times out of 10 you're going to be right anyway. So pause the video and have a go. Okay, so number 1, hydrochloric acid plus iron oxide. So iron is my metal. It's going to be iron chloride because I've got a chloric, hydrochloric acid plus the water. Okay, second time then, the second one, I've got sulfuric acid this time plus the iron oxide. So I've got iron something. It's not going to be iron chloride, is it? Because I've not got hydrochloric acid, I've got sulfuric acid. So it's going to be iron sulfuric. That doesn't sound right. Iron sulfide, maybe. Iron sulfate. That sounds about right, doesn't it? Iron sulfate plus water. Okay, so the third one then, nitric acid plus iron oxide. So it's going to be iron nitric. Iron nitride, maybe. Iron nitrate. I'll go with that one, plus water. And finally then, one that we don't study officially, but occasionally it crops up, and I like to make it hard for you anyway. This one is going to be iron citrate plus water. How did you do? Okay, so the core concepts then for this part of the lesson. So a salt by definition is a chemical in which the hydrogen from an acid has been replaced by a metal. Whenever you use hydrochloric acid, you're going to make a chloride salt, so whatever metal plus chloride. Whenever you use sulfuric acid, you're going to make a sulfate salt, so the metal and then sulfate. And whenever you use nitric acid, you're going to use a nitrate. So you're going to make a nitrate salt, so metal plus nitrate. And those are the only three you'll ever be asked about. They don't ask you about any other acids. So there you go. So in this unit then, at this point, there is a required practical from the exam board. So OCR would expect you to know this practical inside out. You should have done it in class. I would watch a video if you're not entirely sure on this elsewhere, so you can see it being done. But this is how to make or produce a pure dry sample of salt. And the one that they expect you to know is copper sulfate salt crystals, but they could ask you how to make any other salt, and it's going to be the same procedure each time. Now, it could be that they give you a method and they say, well, what's wrong with this method? Or how could they make the method better? Or they might say to you for 6 marks, write a method. Or they might say, look at this data, what's wrong with it? How could you improve it? How is it going to make it more precise? So you really need to understand this practical. It's well worth spending the time. This is just going to be a quick overview, so you know you need to think about it. So I'm going to make copper sulfate salt crystals, okay, and that's the lovely blue colour if you remember them. So I'm going to use copper oxide. This is a base, it's not soluble in water, and it's a black powder, and I'm going to add that to sulfuric acid, which is a clear liquid. Now I'm going to add lots of copper oxide. It's called adding to excess. I'm going to add more than I could possibly need to make sure that every bit of the acid is reacting, because I don't want any acid left over. So I'm adding copper oxide and I might stir it until it stops dissolving, until it stops disappearing. Dissolving is the wrong word, until it stops reacting. Goodness me. Now, you could do this in a conical flask and just keep stirring it or swirling it until everything stops reacting. But reality is, in class, we probably did this in a boiling tube and we used a Bunsen burner to just gently heat up that reaction. That's because copper is relatively unreactive and it needs a little bit of heat energy just to get everything going. Now, if this was iron oxide or zinc oxide, you probably wouldn't need to do that, but it's worth noting that that is what we're doing here. So we're using the boiling tube and we're just heating it up ever so gently, giving it a bit of extra energy to keep it going, or get it going, I should say. So that's stage 1. So step 2, you've now got this reaction completed and you've got copper sulfate, which is this lovely blue liquid, but you've also got all this extra unreacted excess copper oxide and it's still this black powder. And so this way is where the pure comes into it. I want pure copper sulfate crystals, not mixed in with some black copper oxide powder. And so step 2 is filtration. And as you can see there on the diagram, we are filtering this mixture of the reacted copper sulfate solution. So that's copper sulfate and water. And that's why it's a liquid. It's the copper sulfate crystals are dissolved in the water. So that goes through into the conical flask. And the copper oxide is a powder. It's a solid, so it can't go through the filter paper and it's stuck in the funnel or in the filter paper. And that's step 2. So by step 3, I've now got this gorgeous blue liquid and it's nice and clear because we've done filtration nice and slowly and we haven't poured it in too quickly and it's not gone down the edge as some of you tend to do, and you've absolutely not poked a pen through the filter paper, so it's all gone a bit doolally. So you've now got a nice clear blue liquid. However, that's not a dry sample, is it? This is not salt crystals, this is liquid because you've got these salt crystals dissolved in the water. And so the final step then is evaporation. Notice it's an evaporating basin, it's not a bowl, it's not a dish, it's evaporating basin. If you can name equipment, you're going to gain marks. Okay, so solution goes in the evaporating basin, and the slower you do this process, the better crystals you're going to get. So realistically in the lab we probably just evaporated the copper sulfate, the water, leaving the copper sulfate crystals behind as solids. If we had more time, what you would do is you would gently heat it, and then before your crystals start to form, you take it off the heat and you allow the evaporation to happen ever so slowly over time, possibly put it on the windowsill or put it scientifically you could put it in an oven and let it dry slowly. and then what you get is the bigger crystals. Now this works because copper sulfate crystals tend to decompose when they're heated up too quickly. So if you want nice, great big copper sulfate crystals, you do crystallization rather than evaporation because it's slower. But either of those words would work in an exam situation. So evaporation or crystallization is step 3. Okay, so let's have a look at an exam question here, then a bit of transfer for you. Pause the video and have a go for yourself. Okay, so it says here ammonium nitrate. I don't know what ammonium is, anybody? Ammonium nitrate and potassium chloride are both salts. Okay, they can be made by neutralization reactions. Okay, choose substances from the box to complete the word equations for the formation of these 2 salts. Okay, so the first one then is ammonia plus something making ammonium nitrate plus water. Okay, well, chemical reactions, we always make something new. So if that blank can't be ammonium nitrate or water, can it? Because they're the products. So it's got to be something that allows us to make a nitrate. Because I've got ammonium nitrate, haven't I? So what could that be? Well, if I'm looking in my box, realistically, it could be nitric acid or it could be potassium nitrate. Well, it can't be potassium nitrate because I've got no potassium in the products. So I'm going to go with nitric acid. Okay, this next one then. Something plus hydrochloric acid makes potassium chloride plus something. Okay, so hydrochloric acid, well, it's a neutralization reaction, so I need an alkali, don't I? Some kind of hydroxide maybe. And I know I'm going to make water. Okay, so, and I've got to make potassium chloride. So I need an alkali that's making potassium chloride. Well, I've got a potassium hydroxide there. That'll do. And I'm making water as well. So that's that one there. Okay, so pause the video and have a go at this one. Okay, so copper sulfate, CuSO4, is a salt that has many uses. An aqueous solution, so remember that means dissolved in water, of copper sulfate can be made by reacting copper oxide with an acid. Name this acid. Well, there's only 3 acids we ever talk about: hydrochloric acid, sulfuric acid and nitric acid. Which is going to work to make a copper sulfate? Well, I'm hoping you would recognise it's sulfuric acid. Write a balanced symbol equation including state symbols for this reaction. Okay, so you might have thought, well, how am I supposed to know this? Well, you should have known this because this is part of the PAG, the required practical that you should know back to front. And so even if you weren't sure, you could look at the question. It gives you the formula for copper sulfate. It gives you the formula for copper oxide. You should know water is made. The only one that's not on this page, I think it was on the last page, was the sulfuric acid, but you should know it's H2SO4. So this is just really knowing your stuff. This is the equation. It's actually balanced as is. I've got 1 copper on each side, 2 hydrogens on each side, and 1 sulfate on each side. And it said in the question to include the state symbols. So copper oxide was a solid, it's a powder. How would you know that? Because you need to know your required practical back to front. The sulfuric acid is a liquid. The copper sulfate crystals are aqueous. It says it in the question, aqueous solution. And of course, water is a liquid. I don't know why in the exam it actually said ignore the state symbols, but when it said it in the question, but there you go. Okay, so pause the video and have a go at this one. So the most common use of acids and alkalis in neutralization in daily life is you have heartburn or indigestion, which is acid from your stomach, and you take an alkali or an antacid to neutralize your stomach and to cause less pain. So this is what this is talking about. But the question is, write the simplest ionic equation which represents a neutralization reaction, and you should know it's this one here. So ionic equation, neutralization, it's the same every time. And why does chewing a tablet work faster than swallowing a tablet? Well, it's something along the lines of smaller bits, a larger surface area. It's going to be a faster reaction because it dissolves faster, something like that. Okay, that's the end of today's lesson, guys. I'll see you later.